So I think this is working. Graphing techniques. So what's the whole purpose of drawing a graph? We draw graphs because humans are visual creatures. We take in information best as pictures, and a graph is a type of picture. And when you run an experiment, you're going to gather sometimes massive amounts of data, lots of numbers. And if you put them in a table, I mean, it's valid. I mean, all the information is there, but you can't make sense of it because it's just rows and rows and rows and rows of numbers. Now, computers can handle that. That's what they do. But if we want to make sense of something, run an experiment, and we get all these numbers, it's more effective to create a visual image of it in some way, and a graph is one of those ways that we do it. So we got all this data, we want to put it in a graph, and graphs they run the full gamut. They can be scatter plots, two-dimensional Cartesian system. They can be, with computers now, you can visualize three-dimensional graphs, or you can use statistical analysis and implant that in the graph to show just how reliable you think your numbers are. For instance, let's see. This is a better marker. In the Cartesian system, right, X, Y, actually it can go this way and that way. You have negatives on both axes. This is the x-axis. The abscissa is the proper name for it, and the y-axis, the ordinate. And if we have a data point that corresponds to some information that's of this nature correlated with information that's that nature, then it may present a point up here that is x1, y1. So at this value here, it's x, and at this value, it's y. So that's a data point on a two-dimensional graph. And this is the kind we're going to be working with today. But you take several data points, say, well, from my perspective, if I make this one nitrogen applied, right? If you're a farmer, or you have a farmer in your family, it's asking, they'll know what that means. Put a certain number of pounds per acre of nitrogen on your crop, and you should expect a certain response in its yield. Like if it's on corn, so many bushels per acre of corn, and this would be the yield. If it's corn, we might say bushels per acre. That's not the metric system, obviously. Pounds applied, pounds per acre. Okay, so if we put a certain number of pounds of per acre, we might get a yield right there. Or if you measure it in several places in that same field, you might get several different numbers, but they're close. And then if you put more nitrogen on it out here, then you may get something out here. And intermediate levels, you might get something in here. So if we want to say something about the reliability of those numbers, they have a general trend of increasing yield with increasing nitrogen. So if you use a best fit line, one that has the least deviation, it goes through the middle of all those points, is actually what it's doing. Then you may draw a straight line like this. And the difference between that line and each one of these points is a minimum. You make it as small as possible. The fancy word for this is linear regression in statistical terms. And actually, we'll talk about that in a few minutes. But this visually represents all those data points. Like if you've got several experiments like we used to have when I was working in Louisiana in the field, you'd have experiments scattered all over the state. and you make these applications and make the measurements of yield at the end, among other things. We do plant tissue analysis too, so you get massive amounts of data. And this is one efficient way to represent that information. Now, I've seen graphs that were like, let's see, that's not going to be on this. Like this. I've seen graphs that are like this. And the scientists will draw a curve like that and say, ooh, look how good that fits. And then they'll do statistical analysis to support it and say the R value is like 0.630. If you know anything about R values, it's a measure of correlation, right? That's pretty poor. You need something better than 0.9. Anyway, that's just to illustrate the point that visual representation is an efficient way of communicating the results of your experiment. Because when you publish your information, you want as many people to read it as possible, and you want to convince as many people of your point. So think of it as kind of like, I don't know, mini politics. Actually, most science is politics. And many scientists live their whole career based upon their reputation. And they just, I mean, when you dig down into the, underneath all their experiments, you find out that they're just pure crap. But they float along on their reputation. Okay, so let's see. All right, so one other thing about this graphing system is it's customary for the x-axis to be the dependent variable. Excuse me, independent variable. The independent variable is the variable that is chosen and adjusted and changed by the researcher. And then the response to that change is the dependent variable, the y-axis. So we put our independent on the x and our dependent on the y. And that just says that if we, as the experimenter, if I say I set the value at this one, then the experiment, whatever it may be, will respond with a value up here, say, and then that will be your data point. Okay, let's see. We talked about the axes and their names. This is known as a quadrant. Quadrant comes from the Latin, which means fourth. Right, so you can have other quadrants. You can have one down here, here. You have 4 quadrants. So you can't have negative values. These are all positive values. These are negative values of x. These are positive y's, and these are negative negative y values. So you can have a point down here that's minus x minus y. That's perfectly valid. I mean, as long as it fits reality. Okay, let's see. This is known as the origin, right? What's the XY value here? 0, 0. That's why they call it the origin. Okay, and I just showed you a line graph. Let me scroll. Here we go. Okay, so this is what's known as a best fit line for these data points. And notice that we try to make the line get as close to the points as possible. Minimize the variability, the variation from the line. That's the whole point behind drawing a best fit line. Now, these data points say that we're pretty sure about how things are going to behave in between these actual measurements. And we can estimate values. Once we draw that line, we can estimate values in here. We didn't make a measurement, actual measurement there. Right? But we can use that graph to say, all right, if we want a response of 0.8 for volume, then we go over here And we should expect to do maybe 225 temperature, K. Right, K temperature will give you this volume response. Okay, so that's called interpolation. You're inside the measure points. Interpolation. Sometimes you can stretch it a little bit outside the measured area, and that's called extrapolation. It's a little more hazardous to do that. And if you have a straight line there, and you say it stops right here, and it stops right there, and we want to extrapolate, then usually published work will have this best fit line, and then they'll have another pair of lines on either side. And those are the confidence intervals, right? You have high confidence, and you have to specify, is it 95%, is it 90% confidence in finding values for this experiment. Based on these values, you can probably find them within that range right in there, okay? But as you extrapolate more and more, your confidence limits go like that. You become less confident outside that range. Okay. It doesn't show it on this graph, but it's true. And you use statistical analysis to generate those values, those curves. All right, let's see. All right, so if you've got a set of data, what type of considerations do you need to make when you're going to draw a graph? Right? You got a set of data here, X's and Y's values, and they correspond to one another, right? It's like this is the independent variable and this is the dependent variable. This is the one you change, and this is the measurement you make as a response during the experiment. For instance, we haven't talked about gases yet, but what Robert Boyle did was he trapped the gas and he changed the pressure on that gas, and he noticed what happens to the volume. So the pressure was the independent that he changed the pressure, and the volume was the response to that change. So pressure and volume would be your two independent and dependent variables, and then he graphed them, right? And there's an example of that in here somewhere. He graphed the two, like pressure here and volume here, and he found out that best fit line was like that. Okay, so when you're going to graph something like this, there are certain things you need to consider, right? When you have this data set, it's both for scientific reasons and for aesthetics, because, right, you want to convince somebody of your position. So you want it to be inviting. You want it to be easy to understand your graph. So you take your points and you say, okay, should I present this graph as a portrait or landscape? Okay. If the X values or the independent variables are very long, wide range, you may want to do it landscape and stretch them out like this. And then if the response is a narrower range, right, you may have landscape would work better. But if the X variable is a small variation, range from smallest to largest, then you may want to put that one here, and you get a huge change in your Y value, then the portrait might work better. Then once you've decided your orientation, then you need to look at the range of actual values. And how do you present those values in your graph? Right. So that's what we're talking here with the scale units. What are your scale units going to be? So if you have a graph here, then you want to look at you want to use as much of the space as possible. Okay. So if you've got, say, between 1 and 100 values for X, then you would stretch 100 out to here. And then subdivide it, say, in tenths or 20s or whatever is convenient. And maybe this one only goes to 20. Well, actually, that contradicts what I just said. If this goes to 100, then, and this one's the tall one, this one may go 500. So you have 500 up here. And then you subdivide it in equal units. And if you've already got graph paper, right, with already hatched, then you want to see, well, if I go 500 for the full length, is that going to make evenly spaced units on the way there? If your graph paper is built in such a way that you can go 100, 200, 300, 400, 500, and it only goes to here for 500. And then if you try to add in another unit for each space, it would put 500 off your graph. Well, you got to go to the smaller unit. So you have to think of the total magnitude of your scales, and then look at the subdivisions. Let's see, is that in here anywhere? Maybe it's on the next one. Oh, drawing the axes. Okay. Preparing the graph. Selecting the scale units. Right? You have to know what these units are. And when you draw your graph, you need several items to be incorporated. Think this overriding rule. Graphs need to be self-contained. In other words, if I pluck the graph out of that paper, it's got all the information I need to understand what it's saying without looking at the research paper. So it needs a couple of things. First, title, a descriptive title to say what it is. What are you graphing? The relationship between blah and blah, whatever else. Sometimes you even need to put footnotes. You need, the X has to be, what are the units here? Right? Maybe this one is pressure, but the units will be in atmospheres. And if this is volume, what did you measure volume in? Well, maybe it's liters, maybe it's milliliters, but you need to say what your scale is. And then you need to mark your, let's say, 10, 20, 30. You need to mark these units regular spaced, right? Unless you've got graph paper that's designed to be non-linear, like logarithmic graph paper, which we're not going to mess with, then you just assume that it's a linear progression. So you don't say this is 100, but this is 50 down here. And then you divide this one into 10 equal units, and then between 50 and 100, you can't do that. It's got to be linear unless the paper is designed to manage it. Okay, let's see, what else do we need? You gotta mark off your axes, label them, and what they represent on each one. Then you put your data points in, and you try to draw a curve that matches them. So that should be able to stand on its own with the title. This one probably wouldn't need footnotes. Let's see. If you're going to do this by hand, you probably want to use a sharp pencil or a sharp pen. So the points will be small enough that they won't interfere with one another. And what you can also do if you want is for each one of the points, you can identify what its actual value is. And if you do this in Excel, if you're familiar with how to graph in Excel, you can tell it to put those data points in there, right? Identify the X and Y values for each one. Okay. Let's see. Drawing the best fit line is sort of, if it's a straight line, you're in pretty good business. Okay? Because all you need is a straight edge. And the best kind of straight edge to draw a best line for one of these graphs is one you can see through. Because you can see the ones that are outside the edge. But if it's opaque, you can't see the ones that are under. So it's a little harder to get it exactly on, unless you do it like this. Lay your ruler like that. You can look on either side and adjust it to get minimum deviation for each one. And then once you found it, you can lay it flat and draw your line. That's a possibility. But I like the kind you can see through. Now, drawing a curve is a little more tricky. You might need a large, what they call a French curve. You've seen those in a graphing kit. You always got a ruler and you got a compass and you got usually have a French curve if it's expensive. It's a piece of plastic that's got a decreasing radius curve. So it goes along like this really quick. So you got different radius curve and you can adjust it depending on how your points curve. If they curve gently, then you'll use the large radius part of the French curve. And if they curve fast, then you just rotate it around to use the smaller radius curve. That's the way we used to do it before computers. In fact, we used to use an ink pen called a rapidograph. It's a special kind of pen that would deliver a uniform amount of ink in a very thin line. It had a tip with a plunger in it, with a very fine needle plunger in it. And it would only deliver ink when you pushed down in that plunger, and then you drew it along. If you picked it up, then the plunger was slammed shut, no more ink would come out. And they were expensive, of course. Okay, let's see. We talked about interpolation, extrapolating lines. In fact, we talked about temperature. Did we talk about temperature in the first chapter? Measurement systems. Did I talk about how Kelvin came up with his system? Where he took the temperature and volume of gases and drew the line, and it came down to here, and then he extrapolated all the way down to find absolute zero. That was kind of a stretch because he had to extrapolate a long way to get there. So what's the slope of a line? When scientists plot their data, they prefer straight lines because the straight line is very well defined. It's well behaved. Curves don't behave very well. They can have almost any equation that describes it, but a straight line is fixed. I mean, it's got one equation and only one type of equation that describes a straight line. Right? Say if it's going this way, it's y equals mx plus b. Y is the value of y, x is the value of x, m is the slope of that line, and b is the y-intercept. Where does it intersect the y-axis? Right? Straight lines are very well behaved. So that's why transformations are a common way that scientists make sense of their data. They take their data and convert it in some form, some way, to make it behave like a straight line. So how do we find the slope of that line? Well, you need a data point, either a measured point here or one that's drawn from the best fit line. And this gives you an x value. And this gives you a y value. And then you need another point on that line. Right? So that gives you another value. And that gives you another value here, y2. So what's the slope of that line? I always think rise over run. So the rise is the y distance here. And that's y2 minus y1. And then the run is x distance. Right? It's just x2 minus x1. So the slope, m, is going to be equal to the change in y divided by the change in x. That's the slope of the line. That just tells you how steep is it. I mean, if y is a huge number and x is a small number, then it's going to be a very steep slope. Whereas the reverse would be a shallow slope. And if it's a positive number, it's going to slope that way, up to the right. If it's a negative slope, it's going to go the other direction, like that. So that slope can tell you a lot about the line. Let's see. All right, this also tells you that x and y are directly proportional. Yeah, directly proportional. Now, that doesn't mean they have to be linear. Direct proportionality can be derived from a curve also. But in general, you see an increase in x relates to an increase in y. They're directly proportional. So it could be like that or like that, and still generally that way. Whereas inverse proportional would be the other way, like this. Or Boyle's pressure volume. Boyle's pressure volume would be that way. So generally speaking, it's as pressure increases, volume decreases. Right, that's inverse proportional. Now, if you, does anybody in here had calculus? All right, oh yeah, okay. So you understand what I mean by instantaneous slope. The tangent to that line right there is the instantaneous slope of that line at that point. But down here, it might be like that, or up here, it might be like that. But all of those straight lines are negative slope. Okay, let's see. So that's how you calculate the slope of your line. And then, of course, if you want to find the y-intercept, you can either do it visually, right? Just draw an extension down here and find out where it intersects the y-axis. Or you can pick two related points here, plug them into your formula. After you know what m is, if you plug in x and y that are related by a data point, then you solve for the unknown and you can find your slope. Okay, it's like any equation that's in one unknown, you can solve it. So that's usually what you do. Right, you find out what the slope is, then you plug in x, y, and the slope, and find out what the y-intercept is. Let's see. Okay, I've talked about all that stuff. Yeah, there we go. Yeah, that's everything there. Okay, I talked about transformations. Let's see if I should have a hard copy out here so I can look at it while I'm going. So I'm going to skip down. I think there's a graph. Nonlinear relationships. Here we go. So this is what, let me scroll a little bit finer than my pointer can do. There you go. So this is a plot of Boyle's experiment. Pressure down here, which is the independent variable, volume is the dependent variable. And the best fit curve is known as a hyperbola. Remember what hyperbola is? Well, there's a formula for calculating it, but general characteristic of a hyperbola is it's a curve that never touches either axis. It just goes on infinitely out here, getting closer and closer and closer, but it never touches. That's a hyperbola. Hyperbola is also a conic section, but we'll talk about conic sections maybe later if it comes up. But notice this is a curve. I mean, how do you define that? Well, a good mathematician could, but in Boyle's day and nowadays, it's very easy to transform the data into a straight line. Okay, so here's how we do it. If you've got pressure and volume, like this, and as the pressure goes up, the volume goes down. What if we take the inverse of volume? Right? As this one goes down, if we take the inverse, it should go up. Right? Why? Because 1 over V, if the denominator gets smaller, the inverse should get bigger. Right? The denominator gets small, divided into 1, makes it bigger and bigger. Right? So we take 1 over V and we plot 1 over V against pressure. Right? So the units here before, let's use the units we had before. This is still atmospheres, right? So if this was, let's be consistent here, volume liters, okay? If we're using volume in liters, then what would the units of measure be here? Be liters to the -1. Be the inverse of liters, right? So now if you plot it, instead of going this way, it goes straight line, right? And you can see that from plotting the data. But what does this mean about how do we define that line? Well, if we say y equals mx plus b, then the slope is going to be rise or a change in 1 over v divided by a change in pressure. Okay. So how does it relate to this thing right here? Well, I'm going to jump ahead. We haven't got to gases yet, but I might as well. What Boyle found was that pressure he measured times the volume at each point in his experiment is equal to a constant value. That's his law, Boyle's law. So look what happens if we put volume, right, if we divide both sides through by V. Let's do that. That's mathematically proper. Both sides get divided by V. Okay? I can do that. So this cancels that V, and it leaves this V on that side. But if we factor those out, we can say P equals K times 1 over V. So there's your X value, there's your slope, and there's your Y value. What's the y-intercept? It goes through the origin. Okay? So that's why this works as a straight line. And let's see, let me scroll down and they show you the plot here. There you go. So if you take 1 over V, which they did in this data set up here, and you can't see my cursor, but it's down below that squiggly arrow right down here. You can see V and 1 over V. And when you draw it like that, the units of measure for V, 1 over V is liters to the -1. That's important, right? Units. The variable is 1 over V, and the units of measure are L to the -1. And there's your title. This is pretty well described. All right, you can stop me anytime for questions. Let me see, how am I doing on time? Coming up on 3 o'clock. When are we supposed to vacate? 3:50. Okay, good. All right. So this is, we probably don't need to spend a lot of time on this one. This is another example of plotting data that's a curve and then transforming it. Oh, this is a log transformation. I don't think you have an example like that in here. And if you do, it's probably extra credit. I'll show you the, this is a introductory discussion. So we'll actually look at the exercise in a minute. Let's see. Is this talking about kinetics? Time, yeah, time and concentration. All right. So we're not going to spend a lot of time on this because you don't get to kinetics until the second semester. All right. I better check before I say that. Yeah, I think it's 102, 104. We get to kinetics. Yeah. Which is just rates of reaction. Let's see. You can have some really weird shaped curves. And this one, let me move it up a little bit more. This one is known as an acid-base titration. This is a typical acid-base curve. Right? It does this for a while, and then it goes there, changing slope here, and it's really steep, and then changing slope there. This is known as a sigmoid curve. Looks like an S. This type of curve is in extra credit. You've got two sections in this exercise, the required section and then the extra credit section. And this will come in the extra credit section. This is known as a broken plot. Right? The experiment that's performed goes along fine here, and all of a sudden it goes changes to there. And you have some points in here, but most of it, the best fit line actually fits these curves, these lines down here and these down here. That's extra credit too. Okay. So here we get to the exercise itself. And the first part of it, that's worth maybe a point apiece. Not worth a lot. There it is. These are just definitions, so they're only worth a point. Just see if you got the definitions in tow. And then you actually have to start thinking. Let's see. All right, this section determines whether you understand the difference between dependent and independent variables. This is a plot of volume and temperature. That's another gas law. That's Charles' law. And actually, as you increase the temperature, what happens to the volume of the gas? It increases, right? So they're directly related. So this one should plot a straight line. But notice that temperature here is, there are some minus degrees here, right there, there. So you have to consider, how do I draw my axes so that I can get those values into, right? Temperature is the x-axis. You change temperature and watch the volume. So in that case, you need to draw your graph like this, with some negative space on the x-axis, because this is temperature in degrees Celsius, and this is volume, probably in liters. So you need some negatives out here. Right? That's 0. So you need some negative values out there. And when you draw your graph paper is like this, you need to put the ordinate in the middle of the page. And draw a dark line there so you can see where it is. And that will give you some negative space on the x-axis to work with. Okay. If you draw this on the left edge of the page, some of your values are going to be off the page. Okay. These are considerations when you're drawing a graph, right? You need to plan ahead. Okay, so let's see. And then when you draw the graph, you're going to use the graph to answer these questions. At what volume would the helium sample have a temperature of 5 degrees? Right. So after you draw your graph, then you can use the graph to say, what would the volume be if the temperature were 5 degrees? So that's one of those cases where you didn't actually measure at that, but you used the line, the best fit plot, to say what would it be at that temperature. So when you have a line like this, right, and it says, what volume would it be at that temperature? Well, let's see, if it's at this temperature, then you go up here, right there, and you go across here, there's your volume. Okay. Okay, here's a good one. What would you do with a plot of the inverse volume for Boyle's law as L to the minus 1, and then down here's pressure in atmospheres, right? And you say, what volume would it be at this pressure? Well, you go up here, but you got your line, you go up here, you go across here. So what is that value? That's 1 over V. So it's going to be like a decimal something, like 0.213. That's 1 over V. So what's V? Just take the inverse of it, right? Okay. Got to know how your graph is built and what these things mean in order to extract information from it. If you just put that down, it would be wrong, because that's liters to the minus 1. That's not liters. Okay. Just a word of caution. Okay. Let's see. This is pressure volume, right? So you're going to have to draw a graph. Right? That's what this one is right here. Draw the graph and then use it to answer the rest of the questions. Okay. This is a bonus section, so you can take it or leave it. If you feel adventurous, this is a titration curve. You're going to add sodium hydroxide to your solution. So that's the independent variable, x-axis. And then the y-axis is the pH, which is a measure of acidity. So you don't have to know what these mean to draw the graph. You just have to know which one is the x-axis and which one is the y-axis. The x-axis is the base, this sodium hydroxide right here. So, yeah, we're going to do it. Oh, there it goes. That's the x-axis. This is the y-axis. Right, so you look how far does this go? Right. pH. It goes up to just short of 12. So that would be the maximum part of your scale. And the minimum part would be 3. So usually what you do is you say, if this is 0, then you're going to start your plots at 3. Right? Well, it won't be that, it'll be pH. This will be volume of base. And then you draw do your points here, and then they'll go like this up to 12, almost to 12, and then they'll flatten out for your pH curve. That's what it will look like. But in order to judge what this should be, the maximum is going to be 12. And then this is going to be 0. To accommodate all your values. And then this one is going to be far enough to what's the volume of your sodium hydroxide. So it goes up to 32 milliliters. So you need something that will subdivide your graph paper in units that you can read. Say if your graph paper is blocked off in major units like this, right? And they're going to go up like that, like that, like that, like that, like that. And then you got major units here, like that. Right? And then they usually have finer detail. Like you're going to have subdivisions here, like that. And then very faint lines go up like that. That's typical for graph paper. So your major divisions will be here. And then your minor divisions, you want to set it up so that your minor divisions are close to what you would expect as, say, like decimals of the numbers. For instance, well, for this one, you don't have decimals. You got 5, 10, 15, 20, 25. Well, that's good. But the pH, it could be anything. And when you divide it up, you want to set up your scales in such a way that it's easy to read where your point needs to be. Right? You don't want it to be an odd number so that you have to kind of guess. It's best if you have a line right where your value is going to be. And then you can follow it across easier. So the first time you draw one of these, I mean, you may have to crumple it up, start over again until you get the hang of it. So this is in extra credit section. So if you don't have the time and you don't feel up to it, then you don't have to do it. You're not going to. There's graph paper built in. Oh, there you go. So you got your major lines here, right there, there. Then you got your minor divisions between them, right there. So you decide, what does each one of those minor divisions represent? Right. If this first division is like 0 to 1, if this is 1 right here, then what are the minor divisions? Well, you got 1, 2, 3, 4. You got 5 steps in it. So each one will be 0.2. Just count them off. 0.2, 0.4, 0.6, 0.8, 1. So you're good to go there. This is the way we used to do it, by hand. Doing it in Excel, all this is just, it's in the program. It does a lot of this stuff for you. All you have to do is set the limits, and you can set the minor divisions and the major tick marks, and it'll just, boom, there it is. But unless you know what it's doing, it might as well be a foreign language. And this is how you learn the language. You struggle with it, you do it the hard way. And then when you use Excel, it means something. Okay. Okay, I guess that's it. That's graph paper. So you can take these home and notice that, well, your hard copy, of course, you just write it in and bring it to class or scan it and send it to Blackboard. But if you go on Blackboard and download this version, this fillable form, then you can fill it out in your computer and save it. I think you can save this one. Let me see if there should be a version you can save. Let's see, one. Here it is, savable. So if you open that one up, you can use your Acrobat Reader. You don't need the full version of Acrobat. You can use your Acrobat Reader to fill it in and then save it. I've set it up that way. I have the full version of it. Take to the notes for it. Then you can, and I created these savable forms simply because when we were stranded at home, this is the only way that I could communicate with my students. So I made it so they could fill it in and save it and then send it to me in Blackboard. Now, if you have anything that has to be done by hand, like drawing these graphs, you have to photograph those and attach them to the file. It's extra. And that's the same. Well, it's not the same with your lab reports. When you do your formal lab reports, those need to be in a single document. So don't send me a Word document and then you have some graphs that you created in Excel. Don't send me the Excel file separate. The graphs need to be embedded in the Word document. So if you don't know how to do that, but you do know how to create graphs in Excel, then ask me and I'll show you how to do it. Okay. Any questions? See some puzzled look, but no questions yet. Okay. It might look like trouble in the making, but it's really not that bad. If you think about what you're trying to do, you're trying to express a position based on data. That's what graphs do. And you want to create the graph so that it will convey information to your readers. I always think about when you're writing a report, when you're creating some product for distribution, you always think about the customer, right? Think about if you're going to make money out of it, sure, right? Just think about it. If this is a class where, well, of course, you have to pay money to take the class, but just think about it in terms of, I want to make a profit out of this product that I'm creating. And then it brings it home. Right? I want this product to say something. I want it to answer the question, for instance, that's asked of you. And if it does that, then you're good to go. If you create your lab notebook and you start filling information into your lab notebook, think about it in those terms. Do I understand what I'm writing? Right? Could I go back in a couple of hours and read it and understand what I just wrote? Right? Or if I write a report, does it make sense? If you've got somebody in your family that's willing, let them read it, see if it makes sense to them. They may not understand scientific terms, but they can understand sentence structure. Right? They know if the sentence makes sense, except they don't understand some of the words, that's okay. If it flows, if it makes sense, if it doesn't just bounce all over the place. And you'll have an example to go by. Oh, that's right, I did. Did I print out a? Yeah, I did. Okay, I'm just thinking, what do I have going on the printer? If it didn't mess up, then I should be able to go get your copies now. I'll do that.